You're terrible. Shall we start? So inshallah today I will be continue as far as I can go. I'm not feeling well. So I will push it as much as we can till, and then I will stop. But I will not go beyond 12. So inshallah, let's try to do the max. So before I proceed, let me go back to what we were doing yesterday. Yesterday, I was mostly talking about contraction. Yes? The problem is a lot of people who are working in fixed point theory, they spend their life on contraction. Okay? And if you remember yesterday, the discussion about Piaget and Ziad about D-metric spaces and G-metric, I told you that the mistake was that when you spend your career in one tiny area of the theory, then you don't see the big picture. You're really very... And the problem, really the problem, like the case with Ziad, he has papers that are highly cited. And why they were highly cited? Because at that time, the people could publish. But the moment the people stop publishing in the area, then that's it, it's done. And it's very hard later on to come back and start something. So when you're learning about fixed point theory, especially metric fixed point theory, you may want to have the big picture. If you don't have the big picture, then there is a problem. And I always tell people, always, that people stays between 1922 and 1965. Okay? All their career is between 1922 and 1965. What happened after 1965? Very complicated. The people don't touch it. They like contraction. And different types of contraction. Because it's easier. You have the iterate, converge. There's nothing. So today, inshallah, I will touch on 1965. I will finish first 1922 to 1965, touch on 1965, move on. But the bulk and the beauty of what happened after will come, inshallah, tomorrow. Okay? Tomorrow I will show you that. Now, where were we? Of course, there is a lot. I cannot spend, I'll be honest with you, even 5 days talking about 1922, 1965. Too big to be done. So what I did, I chose some parts of the fixed point theory that somehow has some parts that have some interest to us, just interest. So we talked about Banach contraction principle, and we talked about Karisty's idea, and we talked about variation principle, and how I didn't talk about Eklund variation principle. What I did is to connect the Eklund variation principle with Karisty fixed point theorem. Okay, so I connected the two. So let me finish by looking at James' advisor, Art Kirk, who asked if this is true, the problem there. The original problem asked by Kirk is the one that you see there. What if I replace the distance from x to tx by the square? Okay? What happens? Okay, so first let us try to understand. I spent a lot of time on this problem. So first of all, what's going to be a problem? So we have before, we have without the 2, d of x tx less than. That's carries t, yeah? Huh? So now we have a square. And what is the problem? So in order for you to grasp it and to understand it, you need to go to Brownsted order. Okay? You have to. If you don't go to Brownsted order, you will not see the inner working of this problem. Okay? Brownsted helps you, and I showed you how the minimal element of the Brownsted order helped us connect Caristi and Eklund. Okay? So it's a beautiful tool that helps you get a profound understanding of the problem. So now, what happened to my Brownsted order? So we have x less than y, x less than y. I want you to extrapolate, read it in your mind. Okay? So what does that mean, x less than y? X less than y, if the distance from x to y squared is less or equal than phi of x minus phi of y. Yes? Or phi of y less than phi of x. I always have this problem between, do I put phi of x minus phi of y or phi of y minus phi of x? Is the reflection of one order, one relation. So the minimal becomes maximal and maximal. So it's not really a problem. Anyway, so what's the problem then? Okay, choose one and start working. What is the problem with the 2? The problem is that the function t squared is not additive. So you will not have transitivity. You will have what? Reflexivity. It will be a reflexive relation. Anti-symmetric, no problem. But it will not be transitive, meaning x less than y, y less than z, x less than z. And therefore, it's not a partial order. And if it's not a partial order, you cannot use Zorn lemma, minimal elements, and all this. You understand? So the problem is the lack of additivity. Okay? Nothing more. So this is false. This question, this counterexample, I found it quickly. In fact, it wasn't like. So it's artificial. So the answer is no. Okay? So we knew. Of course, I'm talking about this has happened in the late 80s when I got interested into this. So the question becomes now evolved from the original question with the square to this one. Okay? So I asked this question. So the square was R's question. And then I said, okay, fine. This failed. Okay, what kind of function we can put in and have the validity of the conclusion? Of course, if eta is what? Additive, then the problem becomes obvious. So the issue is not about additivity, except if you prove to me that the only way you can get a positive conclusion if eta is additive. So remember again, it's very important. Why are we interested in the additivity of eta? It's because of this relation. Do you see it? So as I said here, if eta is subadditive, then this will define a partial order. And therefore, I can use what? I can use the argument techniques we developed for carries. Is that clear? So the question now is, what happens if eta is not additive? If eta is not additive, let me give you a secret. If eta is not additive, what you have here is a relation. In fact, is a graph. X is connected to y if and only if you have that inequality. So we are getting what? What's called oriented graph. So graphs are an extension of partial order. Okay? Graphs are an extension of partial order. Not any graph, but oriented graph. In other words, there is an edge between x and y if x and y are comparable. Okay? So you put a direction if x is less than y. Okay? You go from the small to the larger one. You put the arrow, so it becomes an oriented graph. So this happened when my plane was landing in Jeddah. Okay? I was in the plane coming from New York, and I noticed this. So now I saw the connection with graphs. So partial orders are gone. Now I'm working with what? With graphs. So the question is, what is the analog to a minimal element? Now, you have to understand, why am I interested into the minimal? For the reason I mentioned yesterday, that T of x will be less than x, and therefore, if I have the concept of minimal in this context, that T of x must be equal to x, and therefore, x is a fixed point. You understand now? So, the problem is, we cannot talk about minimal for a graph. Yeah? So when I landed King Abdulaziz University, and I asked them, is there anybody in graph theory? Okay? The answer was quick, none. I wasn't staying at King Abdulaziz University in Jeddah. I was going to King Fahd University. Okay? So I flew to King Fahd University, and I asked, is there somebody who works on graphs? And they told me yes. So Munzir, he was a wonderful mathematician who did his PhD in graph theory in a wonderful school in Michigan. So I went to see him. It's very important, this point. I want to insist on it. You will see why. And I was told he's no longer practicing as a professor. Now he's in the administration, okay? Taking care of student affairs. I said, okay, fine. I have only one question to ask. So I went to the Dean of Student Affairs office. He was Associate Dean. And they waited. He told me yes. I said I wanted to meet Dr. Munzir. I'm in maths, and I want to ask him something. Okay, after a while. He was busy with students, so after a while, I went inside. And I explained to him my problem, the one that you see right there. So he looked at me in a polite way, and he said, Dr. Amine, I'm really sorry, but my mind has been disconnected from mathematics, and it's just so much on student affairs, student problems. It's hard for me to focus on your question. Okay, fine. this question went unnoticed for 3 years. 3 years. And then, which I will be touching today on, Mundar is no longer associate dean, he's back to the math department. And when I heard that he's back to the math department, I went back. So, hey, how are you? So what I did, I went again to see him. And they said, Mundar, to my question, okay? I have this graph, I have this relation, it defines a graph, and I'm looking for the concept of a minimal. What is the analog to a minimal for? Now, I wanted to understand, and Izhar knows what I'm talking about. This was the beginning of an amazing relationship that now, in the world, connecting graph theory with fixed point theory is Monotone. Imagine for a second if I did not insist on asking this question. Wallahi, it was exactly what you see there. This question, I kept hammering it. After 3 years, I wanted absolutely to see what's going on. And just for your information, analog to minimal is the root in graph theory. They call them roots. But anyway, the point is, the authority now in the world for bridging graph theory with fixed point theory is Monotone. Amazing what he was able to do. We did some work together, but that wasn't the point. I wasn't interested. I just helped him develop that bridge. So my point is, some of you did not attend my first talk, is sometimes it takes time. It's not fast food. It's not TikTok mentality. It's not like, oh, here's a question from my advisor. I need the answer this week. Or I need the answer by next week. It doesn't work like that. It really does not work like that. Sometimes you have to quit, come back. Quit, come back. Sometimes it takes years before you can see the things fall together. Do you see my point? Or I'm bothering you? I'm bothering you. Okay, I'll move on. I'm going to move on. Okay, so what did they say? Eta is not what? Additive. Okay? If eta is not additive, this is no longer a partial order. It is a relation. Okay? Great. So, something very interesting happened. Truly amazing happened. And I want to share it with you. Now, what happened if, remember the idea of the level of energy? Do you remember? Yes? What happened if we take the infimum? Huh? Remember, phi is always has a lower bound. Yes? Huh? And therefore, we have an infimum. Because we are assuming we are bounded below, and therefore we can assume it's positive. And you have the infimum. Huh? Great. If you have the infimum, think in terms of what I told you, the energy level. Okay? So if you are at closer to the infimum, to the lowest energy level, closer, you are going to find the particles there. That's the definition of the infimum, yes? Take the infimum plus epsilon. You will find an x such that phi of x is less than infimum plus epsilon, bigger than the infimum. Yes or no? Okay. What happens if now I take T of x? Now, what did I tell you yesterday? Which is still valid, by the way. What happened is that T of x will have its excited particle, but the level of energy at T of x is less than the one at x. Yes or no? Because this is positive. This is positive. Therefore, this is less than this. Yes? So when I put T of x, phi of T of x will be less than phi of x. Therefore, if phi of x is less than the infimum plus epsilon, phi of T of x will be also less than the infimum plus epsilon. What does it mean? It means there is an area, certain level, where it's T invariant. If x belongs there, T of x stays there. Do you see it now? And why is that? Why is it that important? Because if it is x and T of x are there, what happens to T of x minus T of tx? So now, the numbers are between what? Between infimum plus epsilon. Yes? But so when you take the difference between them, if you are in that set, what is the difference between the two of them? It's going to be less than this minus this. Yes? This minus this is equal to what? Oh. So phi of x minus phi of tx is less than epsilon. Are you with me? So, see, it can be any number what? Positive. So, remember, I'm working on m. Let's call it m sub epsilon. M sub, this m, call it m sub epsilon. So what is m sub epsilon? Is the set of x such that phi of x is less than the infimum plus epsilon. Are we in? What happened to that m epsilon? It's invariant by t. T of m epsilon stays in m epsilon. Therefore, I am not looking at T over the entire metric space. I'm in a certain region where I squeeze my particles close to the lowest level of energy. You understand now where I'm going? What do I know about phi? What is special about phi? Is lower, so my continuous. Guess what? If it is lower, so my continuous phi, the m epsilon is closed. So if xn converges to x, or xn converges to omega, phi of omega will be less than lim inf of phi of xn. Since the phi of xs are all less than the infimum plus epsilon, the other limit, phi of omega, will be less than the infimum plus epsilon. So it is closed. Since m epsilon is closed and m is what? Complete, m epsilon will be what? Now, let us translate the problem differently. Pay attention. Same problem, but I am not in the entire space. I am in a region where phi of x minus phi of tx stays less than what? Good job. And epsilon, I can choose it what? As close as I want to what? 0. Not equal to 0, but as close as I want. So now look at this now. So it gives me an idea of what's happening in the next slide. Wallahi, is exactly how I took it. What I'm telling you is exactly what happened, step by step. So, now, this we said what? In that region, this will be less than what? All this. Epsilon. Therefore, this one will be less than what? Epsilon. So now I have a function, eta, of some numbers less than epsilon. What I want is this will force what's inside to be linear somehow. Phi will be small. Yeah? Phi will be small. I want the inside, the variable, to be linear. Okay? How do we get that? We get that if the derivative of eta is what? At 0, not equal to 0. Okay? So remember, by the way, I forgot to mention, eta of 0 is 0. Because it's from the condition there. Take x equal y. If you take x equal y, you will get what? Phi of x minus phi of x 0, 0. Eta of 0 will be equal to 0. So eta of 0 is equal to 0. And what I want is the derivative not to be equal to 0. If the derivative is not equal to 0, what happens? Close to 0, my eta of t is just a number which is a slope time t. And therefore, what do I have now if epsilon is very small? What do I have here? I have a number, the slope, 0, time, the distance. I am back to what? To Browder. So it's not a partial order everywhere. It is a partial order in m epsilon. In m epsilon, I have a minimum. Do you see it now, the proof how? It's not a partial order everywhere. I can squeeze it, stay in that m epsilon, and there I will find what? A minimal element. These are the ingredients why this was done. Okay? So I defined what is what? The minimum for minimal for that relation. Okay? Which is, as I told you, the root for the graph. Okay? And what you see here is exactly what I just told you. The derivative is positive. So the function eta is increased. Okay, let's go to the original problem of and Kirk. What was it? What was eta? T squared. And what is the derivative of t squared? And what is the value at 0? You see it now? What did we say? It works for what type of function zeta? Additive, yes? So what happened to additive function? Now you have this identity. See it? So it is also true the condition is valid for additive mapping. So it fails for t squared, but it is valid for additive function. Now, do we have an example where the derivative is not equal to 0 at 0, and it's not additive? That's the one you see on the screen. Okay? The derivative is equal to 1 at 0, and this function is not. Now, of course, once we did this, or once I published this, people said what? To improve on the derivative not equal to 0. Okay, so there is work that was done after this. I didn't want to bother you with this. It's just to give you a feeling of some of the problems and how it impacted the research a little bit with some patience. Okay. Second. Okay. Now, I want to talk about something different. Okay? And something that is impacted fixed point theory for years, but it came late. Okay, it didn't come at the same time as 1922, 1965. Okay, it's fairly recent, and it's attracted big attention, big attention. So I want to touch on it, and then I will explain to you why our friend Mondor is considered now as being the leader in bridging the graph and fixed point theory. So in order to start, let us go to what is a monotone mapping, okay, or increasing mapping. So you have partial order, and you have t, so satisfies x less than y, t of x is less than t of y, okay? Monotone mapping. Okay? Now, when we talk about monotone mapping, what comes to mind is Tarski's fixed point theorem. Okay? So it says if the order is good, then any monotone map will have a fixed point. In fact, there is more to the story. Okay? This is old, by the way. This is very old. So you have Tarski, 1955, and you have Knaster and Tarski. Tarski was doing his PhD with Knaster. Knaster, 1928. This is typical. Okay? That at that time, somebody will be working with someone, like, for example, injective metric spaces, Spanish Pakli and the Rangen. Advisor has some ideas, and the student will start working on it 30 years later. So don't be surprised if you see a gap of 20, 30 years in between them at that time. So this is common. So this theorem says what? That if you have a nice order, what's known as complete lattice, and you have T which is monotone, okay, increasing, then T has a fixed point. Okay? T has a fixed point. In fact, more than that. The set of fixed points of T is what's known as a sublattice. Okay? Powerful tool. And if you remember, I told you this is the beginning of what's known as discrete fixed point theory. Discrete fixed point theory. Great. Known, I mean, we know of this. Now, 2002. So, 2002 is Dutch, from Dutchland. And the Sayyid is Egyptian, and he was visiting Iran doing research with him. Okay? And they looked numerical approximations, numerical work, numerical mathematics. They were really doing some heavy computational work, okay? And they were looking at this matrix equation, okay? So, want you, from yesterday, to tell me about this equation. Yalla. Tell me about it. Wallahi, I didn't hear you. What is it? Fixed point equation. Why I'm asking you? Moving forward, every time you have this, oh, this is a fixed point equation. I may use what? Fixed point theorems or maybe some techniques. Do you understand now? Many people don't see this. So this is a fixed point equation. But when they did it, they didn't treat it as a fixed point equation. They worked on it using like properties of Hermitian matrices, and they were able to prove that this equation has only one solution. And one way to find it, if you take the right-hand side as an operator and you iterate it. So let me repeat myself. Okay? This equation has only one solution, x. Okay? One matrix. Number one. Number two, the way they prove this, you take the right-hand side. This right-hand side is like an operator. T of x. And if you iterate T of x, the iteration sequences will converge to the solution of this equation. Okay? So, huh? Yeah, I mean, these are principles. Yes? There is only one tiny problem. It's not a contraction. So, the conclusion, I lied, tells me there is maybe Banach contraction. But when they checked, that operator on the far right is not a contraction. It didn't fly. They did it, but it didn't fly. And they didn't care because from a numerical point of view, they needed the solution. So it wasn't like important to develop a theory behind it. You understand? It wasn't their goal. Their goal was to find the solution. That's what they wanted to work with the solution. Years later, Reurings, she's a student who came to do her PhD with Rand. Okay? And Sayyid was around. So they started working on this equation. But this time, a little bit more complicated. Okay? Not that much. Which is now, instead of having one matrix AFX, or A star F of XA, you have now family of what? Matrices. Okay? So, she looked at this, and what she found out that, in fact, this operator on the right, okay, what happened to it? If you take a 0, x equals 0, okay, what happens? You will get Q, because f of 0 is 0. Okay? So, that is the image of 0. Okay? And now you take the image of Q. Why am I doing this? Huh? Exactly. Okay. Now what they noticed is this operator, like before, was not a contraction. But if you put the right assumption on Q, what happened to this is that there is an order between the matrices. And if the matrices X, that operator is a contraction. This is new, totally new. So now, let's go back to Banach. What does Banach say? For any x, any y, the distance from tx to ty is less than constant time the distance from x to y, which is condition. Yes? Here, no. You have it, but not for any x and y matrices. Only for matrices that are comparable. There is an order, and if two elements are comparable, T of x and T of y, we have this contraction idea. Number one, that operator is monotone. So, of contraction on comparable elements. Are we in? Okay. So, later on, I discovered that Turinisi, who was a famous mathematician, really a beautiful guy, did work on this. But He was in Romania and was not widely known. So these people from Holland did not know about it. I know this. Okay? So here we are. Of course, and Reurings did not know about this definition. This came afterwards. But they had it in their paper. Okay? They were looking at it from a numerical point of view. Okay? So if we formalize it, what do we have? We have M, which is a metric space, with the partial order. So you see, you have M, D, partial order. Okay? M, D, partial order. T is what? Monotone for what? For the partial order. And for comparable elements, that's what you see there. For comparable elements, if X is comparable to Y, X and Y, you have this condition. So we call them Lefschetz monotone mapping. Lefschetz monotone mapping. If the constant K is less than 1, then they are called monotone contractions. Are we in? So far, so good? Yes? Like R. R is the most beautiful example where you have the order and you have the distance, the absolute value. Yeah. Now, assume you have a fixed point. Focus on the contraction. For non-expensive, I will talk about it later, after I'm done with 65. Focus on monotone contraction. Okay? So the goal, and that's what they did, Rand and Reurings, as well as Sayed and Rand, they want to prove the existence of a solution. Therefore, a fixed point, yes? So you want T of X equal what? X. If X and T of X, if X exists, we know by reflexivity of the order that X and T of X are comparable. Do you agree? So if I know that no X is comparable to T of X, there is no way we can find a fixed point. Do we agree on this? Okay? So remember, the partial order we have reflexivity, anti-symmetry, and transitivity. Yes? So if you want a fixed point, T of X equal X, you must have at least an element X such that X and T of X are comparable. Otherwise, it's not going to work. The reason why I'm telling you this, we visited Mian Mondor, a Chinese mathematician who got the medal field medal. And we visited him in Harvard. And we were talking in his seminar. His name is Yao. In his seminar, and his question was, why are you assuming there is an X such that X and T of X are comparable? Why am I telling you this? Even the best among us sometimes don't see the small stuff. That are obvious, but they don't see it. This question, I heard it so many times. Why are you assuming X and T of X are comparable somewhere at certain point? But the reason is one I told you right now. Okay? There is no other reason. Because the problem is to find it. Okay? So now, let's take X0 comparable to T of X0. So now I need your attention. Follow me now. I'm going to focus on what? Contraction. This one I will talk about it later. So take X0 such that X0 and T of X0 are comparable. Once I know they are comparable, I can use the contraction on them, yes or no? Because x and y are comparable. So what is the image of x0? They have x0 and t of x0. What is the image of x0? T of x0. And what is the image of t of x0? T squared of x0. Do you see where I'm going now? So x0 is comparable to t of x0. And what do we know about t? Monotone. Therefore, t of x0, t of x0 squared will be what? Comparable. Yes or no? And then another t, another t, another t. So what kind of points I'm dealing with? Remember, from yesterday, come on. So I'm looking at the iteration. And all the points generated by the iterations are comparable. If they are all comparable, I can apply what? The contraction condition to them. That was the condition what? In Sayyid and Ran and Reurings. To make sure that one x0 is comparable to what? To t of x0. That was the technical condition they put on their theorem. Okay? Now, so you have this orbit, Tn of x0, and they're all comparable, and they satisfy what? Tn, huh? With power n. So let me show it to you now. It's the same as what? As Banach. As Banach. So now, follow me now. I wanted to do this before you see it, okay? So you grasp it better. So now we have x0 such that what? x0 is comparable to t of x0. It doesn't matter, by the way, which one is bigger. One sequence will be increasing, one sequence will be what? Decreasing. It's not really. They're comparable. Then what do we have? We have the comparability of what? Of the orbit, yes? And then I can use the contraction because they are comparable. And what you have here is k to the power n. Because of k to the power n, and this is a number, same triangle inequality will tell me that this sequence is what? Is Cauchy. And therefore, if it is Cauchy, it converges. So far, this is all valid. So what do I want to say afterwards? I want to say that the limit is what? Is the fixed point. Number one, you need some assumption of t. T monotone and monotone contraction doesn't have to be continuous. So the limit may not be what? In the case of Ran and Reurings, it happened. In their case, it works. And that's how they explain the solution to their problem. Now, so what's the question is? Fine. We have a limit, huh? Omega exists. In general, omega is not what? Fixed point. Under what condition for omega to be a fixed point? Number one. Number two, omega depends on what? On t and x0. In the case of Banach, what happened? We have, because of the contraction, you cannot have more than what? One fixed point. And therefore, the fixed point is independent of what? Of the initial point. Here, how do I connect? If I take x and y, how do I connect the two? To connect their orbits? You can't. You can only connect if x and y are So if they are comparable, the limit will be the same. Yeah. Tn of x, Tn of y, the distance will go to 0 for the limit of Tn of x, and the limit of Tn of y will be the same. But what happens if x and y are not comparable? So you see, it's a version. Okay. So what are after RAN and Reurings, everything was smooth. It was really nice. Then you had some people in Poland where they looked at this problem and they started looking at what conditions on the partial order for which that limit is a fixed. So you have papers that were published. Oh, no. First one. T is what? Continuous. T is continuous on M. Then you have a fixed point. No doubt. Omega will be a fixed point. What about if T is continuous on the orbit? Because I don't care about having continuity of x and y closed. T of x and T of y are closed. No. Only focus one on x and y, which are what? You see, it's like comparable. Because we have good behavior on comparable elements. And that's why we want to be only on ask me to give an example on a map that is continuous on orbit. I have absolutely no idea how to find one. But it's published. That one was satisfying that if you have an increasing sequence with a limit, the limit is bigger than all of them. In fact, it's the supremum. Be careful. We are not in R. Don't look at it as R. It's obvious in R, but we are dealing with space with a partial order. That's not R. There is no reason for this to be true. So you have a sequence which is increasing with the limit. Limit for what? For the distance. Combining now the distance with the topology with the partial order. Are you with me now? So if you have that condition, and that was seen by people, and Reurings, then omega is a fixed point. Ready? It's not complicated. About the T of x. Yeah? The case of x less than T of x. Or the C. So what do we know about it? It's going to be the supremum. Yes? Therefore, omega is comparable to all of them. So what happened to T of omega? It's going to be bigger than T n plus 1 of omega. Then T of omega becomes an upper bound. Therefore, T of omega is going to be bigger than what? Than omega. Next, you show that omega is bigger than T of omega. And that's how you get what? T of omega equal omega. Okay? Now, so these are what? The assumptions. And you have omega being what? Fixed point. The two. It is. Now, let's unicity. Okay? The uniqueness of the fixed point. when do we have uniqueness of the fixed point? We have x0 and we have the orbit of x0, Tn of x0. It converges to omega, fixed point. Let's take x, which is comparable to x0. Okay? Then Tn of x and Tn of x0 will go to 0. The distance will go to 0. Since this one goes to omega, this one will go to omega. Okay? Now, what if you have 2 points, x0 and x? They are not comparable. What if you have y, which is comparable to both of them? So, Tn of y, Tn of x0 goes to 0. Tn of y, Tn of x goes to 0. Therefore, Tn of x will converge to omega. So, if you have, for any two elements, an upper bound or lower bound, you are okay. Now, I want to show you something here. Now, a little bit far. Let's R2. And what you have to understand is, I just said partial order. Partial order can be as artificial as you want. Define one. You have a partial order. And you assemble on the partial order. X, Y, so Y. Let me do it here. Y equal X. I'm looking at this. Okay? Yes? This set, no, partial order, which is what? If A and B less than 1. It means this point and this point, this one is bigger than this one. Are you with me? You take this point and any point anywhere, they are not comparable. Okay? So, let's look at now increasing sequence. Now you are going to get something interesting. Let's take sequence of points which are increasing. So if they are increasing, they must be in one. Yes or no? Yes? What distance I am taking? Euclidean distance. So increasing sequence segment, this segment is compact. Therefore, my sequence will have convergence. The whole region is not bounded. It's not what? Compact. So this example is what? That under this monotone precision mapping, there is more than what they were doing. So there is something called order topology. This is just an example. And by the way, we came up, I will be talking about this, of something called order uniform convexity. Order uniform convexity. So let's move on. There is to this story that we don't know. Okay. Now, this is our first paper in this area. First, on this model. So what I was interested in, so it was and okay, looking at chemistry. So look at the definition. It's very interaction, how it was done, and therefore we have x comparable to T of x, and you have now. Okay, so our result was about this type under this condition. Okay. I want to show you the condition that if you have a sequence that is decreasing, the limit is the infimum, because in the other one it's just bigger. That was Jashinsky and others. It wasn't equal to the supremum or the infimum. Okay? So this condition for the case of Khamsi tells me what? That if you have that OAC property, then you have a fixed point, provided you have an element x0 such that T of x0 and x0 are comparable. And you understand now why this condition. When you see a paper published in this direction, you understand. If they don't, there is no way you will have a fixed point, period. Seven. Okay? Jashinsky, what he did, the partial orders, they define naturally a graph. But graphs may not be partial order. So he took Ran and Reurings and he gave a graph formulation of that one. That's the paper that you see there. And when you have a sequence that is increasing, you just replace it by what? By a graph definition, meaning what? X less than y. If you have a vertex going, is a directed graph. You need to have a direction, oriented graph. So x going to y, that's what it means. X less than y means x going to y. And therefore you have this path, x1, x2, x3, and you have the path going. And you assume what? That you have an element that is basically bigger than all of them. So he put it similar to the partial order. But what I wanted to understand is this. So in his original paper, assumed that for the graph, the vertices is the entire matrix space. Okay? It's a matrix space. Therefore, between two vertices, may have, look at this example. So if you take this point and this point here, there is no edge between them. But between this one and this one, we have an edge. Okay? We don't have an edge. And we have what? The distance. Because we are in a metric space. So run and put it in terms of what? Oh, we got involved. So what does this mean, monotone? This means that if there is an edge between x and y, there is an edge between tx and ty. So you have what's known as G monotone. And what does it mean to be a G contraction? If you have a constant case such that this is happening whenever you have an edge between x and y. Okay? Remember that we always assume that all the edges, all the vertices, is the entire metric space. Okay. So you have this property. Look at this property. It's very interesting. xn plus 1, you have an edge. Yes? It's oriented. So it's like xn less than xn plus 1. That's what it means. So the limit, if there is a limit, is going to be bigger than them. Yes? So if it is bigger than them, it means I have to put it where? I have to put it to the right. Yes? That's what you see here. Okay? Of course, I don't need the entire sequence. I just need a subsequence. And this is just refinement. Whether you want to work with what? Subsequence or a sequence makes no difference. Okay? But this is exactly the condition I showed you before. And it was done in terms of what? Graph. And now you have this theorem again. Okay? The graphical formulation of the RAN and the rings. This is the main result of the paper by Javid. Okay. This is very important to explain to you because I wanted to touch on this, especially the flower shop, if you remember. As the distance from B to A. Do you remember this discussion yesterday about the flower shop? Since I wanted to buy some flowers for my wife. Yes? Did you wonder why? I'm not talking about buying flowers to my wife. I'm talking about why the distance from A to B is different from the distance from B to A. Did you wonder why? Huh? It's because the roads, when we drive, we don't drive in Euclidean space. The distance between this point and this point is exactly the same as the distance from this point to this point. You understand? This is valid. The problem when we are driving on an oriented graph. And therefore, we are going on the graph from A to B. There is no reason to follow the same what? Path going from B to A. Therefore, the distance will not be what? Same. This graph, the road, that is the basis for your GPS, in fact has a technical name. And I did not know that. It's known as a weighted graph. So what do you do now? You have vertices, you have edges, And to every edge, you associate a weight. In the case of the GPS, is the distance of the connection that you have between this vertex and this vertex. Are you with me now? So what did we do? We took the theorem of Jashinsky and everybody else, and we told them, in fact, we are not on a metric space. We are on a weighted graph. And this is part of what's known as analysis on graphs. They are doing a lot of work in this direction. So we started now to work or push in this direction. Okay? Let's go back to Kirk yesterday. What did he ask James? He asked him to find what? I'm just testing whether you are with me or you are not with me. I spent a very bad night yesterday. Very bad night. That's why you see I don't have that much energy. Right? So what was the question from Art, Kirk, to James? I love you guys. Wallahi, I love you. I wish my students were like you. So that question opened the door to definitely what? If you remember, I told you a window that we discovered crazy things with Khamsi. Crazy things. And in fact, thanks to Khamsi, that Ekron was able to discover his variation quantity. It's crazy. It's crazy. So my point is, sometimes either you stick to the obvious or you push it a little bit more. So the idea of a metric space with a partial order, a metric space with a graph defined everywhere. But wait. We don't need a metric space. We just need to work on the graph. And it's known as a weighted graph. Okay? But the people who are working on weighted graphs, they never connected what? To a fixed point problem for monotone mappings according to the graph. Do you see where we are heading with this? Huh? So of course I didn't want to teach you what they do. There is a book written by Monotone. So I didn't want to tell you more about what's going on, but I wanted just to show you how, if you push it, if you keep pushing it, you may find something interesting. Again, how do I push it? You cannot push it by staying what? Artificial. You can't. Or for example, have a paper at the end of the week. You can't. So you need to push it, and sometimes you will get somewhere, sometimes you will get nowhere. But that's part of what? Of the research. Are you with me? Tell me. I'm bothering you, huh? Okay. So, I wanted just to touch this. I don't want to spend a lot of time on this. So, let me now move to 1965. Okay? Real business. So the question was, 1920. Mapping. But he so equal distance x, y, isometry. So they are non-expensive, but they are not. the unit circle, and take a rotation. Centered so what is the image of this element? Okay, that is going to be this element. How much do we have here? Okay? So we know that rotations are, okay? And what is special about this? Do we have a fixed point? Do we have, do you see a point that is invariant? No. No way. Except, of course, if your theta is multiple to pi, but I'm taking like 30 degrees. Now, let's look at this rotation in the plane, not on the unit what? Circle. In the plane. Okay? You understand what I'm saying, huh? So, this goes here. This goes here. This goes here. There is one invariant point, which is what? 0, or the center of the rotation. Yeah. So you see, if I look at it in the plane, I have fixed point. But if I look at it on what? On the circle, no fixed point. And it is an isometry. So it is non-expansive. And the circle is compact. Beautiful. Okay? Not only complete, compact. It will not help you. So they knew this. Okay? They knew that, and also what happened if, so this tells you non-expansive, huh? Will not give you a fixed point. What about if I have what they call strict, contractions? Not contractions. In the old days, it wasn't with constant ellipsis k. What? So this one, you need kind of compact. Because T is compact. If the domain is compact, the minimum between x and T of x, and you are done. So you take what's known as the displacement, minimal displacement. So what is the minimum displacement? So it's inf of the distance x dx, x in x. So they call it the minimal displacement. And what we want is that this minimum will be equal. Well, and we achieve 0 somewhere. In general. Okay? But if you have and be achieving this somewhere, and that somewhere will be a fixed point because of this condition. Do you see it? Huh? Okay. Now, what is the difference between the rotation and the rotation everywhere? I want to tell me. Wallahi, I didn't hear you, sorry. No. Of course, it will work if I have strict non-expansive there. It will be nice, yeah. But no. Anybody else? It's very important. What's the difference? Again, my question. Wallahi, I didn't hear you, sorry. one, the rotation has no fixed point. One, the rotation has a fixed point. Your friend was it. Very important. It's inside the circle, yes? So, if I take this, pay attention. Huh? If I take this and this, will it work? Therefore, I must have center. Therefore, I have to assume what on the domain? If you vex it on the domain, we are no longer in metric space. We're talking about 1965, not today. I know what to do in abstract metric space. 1965, they did not know what to do. So for them to go from a metric space to add convexity to it, we go to what? To a vector space. When they start looking at it, they move to Banach space. No, this was known. And by let me stay with what I'm going to show you throughout after 1965. Ready? Let me show you. No, this is just in a Banach space. What is mapping? Huh? In a Banach space comes what? Huh? The distance becomes the norm. Yes? So this was going on in the 60s and the 50s. Okay? This part is vital. What you see on this slide is vital. It's connected to what I wrote there. Now, look at this. So we have T from K to K, and look at this. Why T epsilon goes from K to K? Why? Yeah. You understand? So we are using domain is convex. In force. Let's continue. There is a fixed point. I'm sorry, fixed point, not in the sense of fixed point theory. It's like a point. Okay? So and they stay with y, which means what? Contraction. Therefore, fixed point. Wait. How point? Right. What? You know that iteration? X epsilon equal to this, yes? Huh? translate fixed point. Which means what? That this moment is equal to what? The minimum of displacement is equal to what? So guess what? From a numerical point of view, if epsilon is 10 to the power minus 100, I reached the fixed point. If epsilon is 10 to the power minus 100, my x epsilon is the x epsilon close enough to t x epsilon up to 10 to the power minus 100. They are the same. Computing. Then, this is profound. Let's take epsilon for 1 over n. So let's call x over n n. We have xn minus t of xn. N infinity, this goes to where? 0. N minus t of xn goes to where? So this is known as an approximate fixed point sequence. Okay? So, this was 1960. It will not be complete to use what? Is what do we do with this approximate fixed point? If it's compact, then you have fixed point. You understand? Because the subsequence will converge, the limit will be a fixed point. You understand now? What kind of assembly can put are weaker? Still ensure what? That now 2 or 3 slides, but I will not do it. Browder. Can add, let me show you the paper. Exist. But it's not interested to find the fixed point. Trying to solve approximate fixed point sequence. Okay? If who did a paper on fixed point of what? Non-expensive mapping. I'll come back to this tomorrow, inshallah. Is this guy. The paper, I asked the AI assistant, and it says on contractive mapping, but in fact it's not contractive in the sense we know. Contractive on fixed point theory for non-expensive mapping, which means the beginning of point. I'll stop here.
example. So, as if we consider this x with the usual metric, and we define a map T from x to x by this rule, Tx equals to x plus 1 x for all x in x. So, verify that it is a basically contractive map, not contraction. So, maybe just please try. Maybe of course a lot of people know about this example. So, maybe we can try. So, what is the question? T is but it is basically contractive map. Okay. Contraction, but it is a contractive or strict contraction. So that it means that we cannot find out you can say Lefschetz constant which is strictly less than 1. This is the mean. So maybe just maybe let us try this problem. So it has two parts. One is the first of all show that it is a basically contractive map, and another is it's not a basically contraction. It means that you cannot find out a basically alpha, or maybe you can say Lefschetz constant which is strictly less than 1. And of course, this is one of the well-known example. Generally, all people in point theory they refer this example. So maybe just take maybe few minutes. So okay, you can cover also now audience as well. Now you have a solution of this problem, because this is a very well known example from the metric fixed point theory. Is it okay? So let us come to the little bit nice spaces, okay? Because generally things on the real line is always little bit easier than the space of the function spaces. So just I am interested in this example. It's the same thing, because big people, of course, a book from the Khamsi and Kirk. So this is the, if I consider this and now M to M. Of course, this is also basically complete, because it's a closed subset of C of AB. So no problem at all. So this is basically complete. F operating on T is equals to just T times T for one. So basically, and this is expected for or by a closed subset with respect to the same metric. So this is a space of X. Why this is also complete. T is a basically map from complete metric space to complete metric space defined by this. So again we have a basically same exercise, show that basically contraction, but it is a basically contractive map. So this is the difference. Of course, problem is same, but this is generally to throw every time. But when you basically read the book from the means big mathematicians or like that, you have generally examples on this type of this function spaces, or maybe you can say examples on the disk, or maybe in algebraic topology. So just so maybe let us try for this part as well. So question is that is not contraction, but it is contracted. And my space is complete, so that's why this does not have a fixed point again. Of course, this does not have also a fixed point, because this is a basically my complete metric space, not compact. Of course, if it is a basically contraction, then by Banach fixed point theorem, it has a fixed point. But this is not basically a contraction, this is a contractive. So as yesterday I said, for the contractive is so much smaller. So this is not a basically compact set. So if we have a basically a fixed point, so just Tx equals to x, so x equals to x plus 1 upon x, and of course 0 equals to 1 upon x, which is not possible. Which is not possible. But we have to do same thing for the basically this interesting exam from the C of AB. So maybe first of all we should check whether this is a closed subspace of this or not. So this is a simple exercise. So please do it. Whether this is a closed subspace of C. Once it is a closed, of course it is a complete. Maximum of supremum, because it's basically on closed and bounded, so that's why no problem with the supremum. The legal metric C of it need not be complete. So first of all, check whether this is a closed subspace. If it is a closed, then of course it is complete, because every closed subspace or subset of a complete meeting space is complete. So in the second example, we have to do steps. So that's why generally these people, you can say Khamsi and other Jemsky or Kirsty, they do all the things in generally function. So please prove. So did you prove this is a closed space of C of AB? Just few lines. Just use the sequential or maybe some other. So value will be at also that sequence is 1. So that's why this belongs to the basically just is space. So now next is a basically closed also complete with. So now map it is a basically contractive but not contract. Contractive and contraction. Because if it is a contraction, then it has a fixed point because M is complete. That's why in the theorem of complete space. So I think this will take a little time, or can discuss more problems. So now Imdad sir is here. Now he will tell you something about, of course, not fixed point theory, or maybe a little bit outside the basically fixed, you know, GIAN, for large, maybe total. No, overall, Now 5 years is retirement also, so that is you are still so maybe for more than 40 years. Just so he will share the basically some his experience, and of course not for research, for teaching as well point of view as well, and some important things about the basically fixed point theory. So I invite Invar sir just to share few ideas with regarding this term. Yes.
In fact, you can say that this is an arrangement as opposed to the engagements of professors. I was not prepared. I was asked in my early days, my seniors, my teachers, that you should not go to the class without preparation. Or if you go to the class without preparation, it is something very similar to a crime, committing crime. So I am here before you with any preparation. Because I was told in the morning that you have to engage, I have to talk to you. So I have come to have the conversation. Maybe I cannot very technical. And at that very stage when you are away from mathematics, as you know, its name is mathematics. But its better name you can say Riyazi. इसको कहा जाता है रियाजी. जैसे if you look at this department, it is termed as शोबे रियाजी. It means mush, practice. If you don't practice mathematics, you will be definitely not that good, not that confident as you see, because you have to be always in touch, in practice, in mush. Urdu में लफ्ज आता है mush. Riyazi means riyaz karna. Anybody used to, this is a riyaz. And as I am not doing anything, I am away from mathematics for the last 4 or 5 years. So obviously, and at the same time, to come and my experience. So I have come to share my experience, what way I come through as far as the academic life is concerned, because some of you are beginning the academic life, and obviously I see very senior persons also in the audience. So what will I say? That will not be for the seniors, because they are already learned a lot of mathematics, but it is for my young students who are here. I will have some of my experiences during the years of my teaching here. I will ask you, I will invite your attention if I ask cross topology the first time in life. Starting your studies up to here, when you come across topology first time, what is your reaction? Topology से आपकी पहली मुलाकात कब हुई, क्या जवाब देंगे? This is a very simple question. तो क्या कहेंगे आप? जो भी हो आप फ्रैंक बोलिए. देखिए मैं तो है खमसी साहब को आपने देखा, ही इज अ वंडरफुल स्पीकर. आई हैव नॉट सीन मेनी स्पीकर्स लाइक हिम, मे बी 1 or 2. We all are teachers. We must know our limitations. A person must know his weakness first. The strong points are always your strong points. Don't focus on your strong points. Always focus on weak points. What is your weak point? And try to consolidate your weak point as a strong point. Try to transform it to your strong point. This I will share my teaching experience, what way I will go through this, and what experiences I have. So this is one of the experiences I am asking you, that how will you say when you come across topology first time? SC, or you are in MSc final, or somewhere you are teaching mathematics. If I ask you topology, when you come across topology first time, what is your answer? Some of you? There are two kinds of teachers. These days our teachers are not allowed to fish out the things from the students. Like Professor Khamsi is very good. He is trying to fish out the things from you. And this ensures that you are in, that not as if you are away. So you have to keep the students involved so that he may not be out of the classroom. Like here in algebra, some time back, he passed away, just passed away. His beauty of his teaching was that he cannot allow you to be away. So he will as well ask you a way of teaching is what? Try to from the students themselves. And that is the best way to teach students. You as a teacher, what feeling you have? To this very question, when you come across topology first time, as a teacher, when you realize? और कुछ? Yes, yes. You are very near to the correct answer, but it's still not 100%. It's not the 100% answer, but he is quite near to it. Yeah. Mm-hmm. Yes. Counting numbers. It is very difficult to, when you become a teacher and you started teaching students, then you must have this feeling that what is the topology, how it came out, to realize it, or when I have to say it, that here is the topology. Whenever you say something is open, whenever you say the open interval AB or open interval 0, 1, there is a topology. And when you say that, you cannot say. Realizing the difference, you say here is the open without carrying it. Because real line is open interval may not be open because you may have the topology. Because you have also many. What will you say? There is also a topology. That very topology is fixed. So what you say in all earlier mathematics, starting now from the school, we have the topology. The best thing is to realize that talk of anything open. So on so forth. The topology, what I want to make a point, what I realized during my teaching, this I have not read anywhere. This is, I am saying, is in mathematics, topology is everywhere. You cannot say that here is no topology. You are teaching, so have the topology. Because what the topology fixed, that is what you topology, open interval topology, as you have, which you can metric topology, as you have later realized, introduced metric spaces topology. The topology is there in calculus also. Topology, that is a natural. Go next. You have the metric spaces, and then you define the topological spaces. There is a considerable improvement that here is topological spaces. What you do, that every metric space is a topological space, but every topological space need not be a metric. As you have read in the MSc, if you look at this, can answer this question. So what you say, every metric space is topology, the topology is standard, that is open ball topology. So whenever you say, what we can say, every metric space is a topology. Varying. So in topological space, whenever you study the topology is varying. You write xt is the topology, means this t is varying. If you take a metric space, a topological space, its topology is fixed. It's not varying. And whenever you say enormous space, look at every inner product is a topological space. That too, the for openness, closeness, compactness, these properties, such properties. So obviously we gain because your object class of, so you have the class of, now you have the class of spaces, and it's far, and you see. You start from a metric space, is still you are losing. Topology have in the topological setting. Why? That what we look relatively smaller class spaces to the class of topological. Since most of you have learned a lot of mathematics, then you have always the uniformizable topological spaces, or a topology or a topological space where you have metrization. Metrization means what? That you have a topological space, you have a metric on this, your metric topology, and then you have another. Sorry, topology. Space. Here, as I see this very department, UGC. But if you try to correlate this, distinguish between Yes. Anything like uniform continuity or uniform convergence and uniform continuity. But if you go beyond, this is not available. Like in topological space, convergence. It is open and contains that very point. This is one. Most standard book is Kelly. These days there are many books. If you look, my personal point of view, Munker's book have been, when you some mistake, it is your mistake. Rectify your mistake. Like I have taught calculus by the book of Piscano here. I have been taught by three-dimensional geometry by the book of G.R.T. Bell. I have been taught analysis in B.Sc. by William Apostle's book. No Indian book was used over here. These days we are not that very cautious, but we should be cautious. Because those books which are standard books, they are error-free. Maybe our books are also good, but there are chances that there are fundamental mistakes in our books. That is the reason why we use books from the standard authors, and there are certain books which are free from the boundary. They are used globally. Like look at the major theory. Many standard books, they are all from foreign authors. Maybe one or two books have by authors, but you have to be careful by using those books, because there are subjects where many good books written by our authors are not available. That is what is there. So what I realized during the course, while going through this, that it is very dangerous to change the book in the course you are preparing. One thing is what here, that what are the syllabi that we should be very careful these days, that what should be our syllabi. And there can be no better entity, better person to choose the syllabi is teacher themselves, because teachers know what to do and how to do and from where to do. Because mathematics is a subject where you must have the background, means इसको मैं हिंदुस्तानी ज़बान में कहूँ तो पिछला सबक याद होना चाहिए. अगले सबक के लिए आप लोग समझ रहे हैं, अगले पार्ट के लिए पिछला पार्ट याद होना चाहिए. ऐसा नहीं है पिछला पार्ट याद नहीं, आप चले आए, आप टीचर से उम्मीद कर रहे हैं कर दे. ऐसा होता है आजकल कि वो पिछला कुछ भी याद नहीं है, आप टीचर बेचारे को ब्लेम कर रहे हैं, कुछ भी नहीं पढ़ा रहा है, कुछ भी समझ में आ रहा है, कुछ है. हमारे यहाँ पे डिपार्टमेंट में हमारे सबसे फेमस टीचर जिनके बारे में लोग कहते थे, जो सबसे ज़्यादा मेहनत से पढ़ाते थे, कि भाई कुछ समझ में नहीं आ रहा, तो ये फेयर नहीं हो टीचर के लिए. So you have to go to the level of the student. That is the best thing, as you have to say. Every teacher has a different way of doing it. As I mentioned about our algebra teacher, he has his own way. I have seen in the class, he used to come, he started displaying with something, and thereafter you say, no, it is not happening well. I will come tomorrow with further clarity. I have said many times to him during his younger days. But definitely, if you look at his competence, that was unquestionable. So we have to be very, very involved in our subject as good as possible, as I have said. The point is turning away, what you say, that topology cannot get you uniform continuity and uniform convergence. Why? Because it has the size of the, it requires the size of the neighborhood. Then the question is that can we retain this somehow beyond metric spaces? Answer is yes. And what is answer is offered by another notion defined by Andrew Weil, that is uniform spaces. Some of you have heard uniform spaces. Uniform spaces can retain uniform convergence. Still there are many classes, many topological spaces which are not uniformizable, and still there is this very diffusion. I don't want to be technical, as I said, I don't want to give technical statements, but using the axioms of both topological spaces and metric spaces, we define the idea of metric spaces. We are showing two classes, extra the journey as a teacher, you see, in many courses you teach. Like another experience I had. How much time I have taken? 10 minutes. This is the hard part of mathematics. That is what during my teaching I enjoyed most teaching living. That's the most challenging and difficult course, and it's not so difficult. But if you look at the ideas are simple. So before you start undertaking or teaching anything, you have to always be very careful that what is the underlying idea. Like if I define the measure, some other things. But let me go back. As Javid said, I will talk something about fixed point theory also. Sometimes working with mathematics, you can get something very simple and very important. I would like to draw your kind attention to the paper of Victor Baryanth. Victor Baryanth has proved in 1968, which is the part of your syllabi in all the books. That is what, if the iterate of a map on a complete metric space is a contraction, still you have the fixed point and you still have the unique fixed point. Look at this very result. This has come in 1968. This is not a very old result. This has come in 1968. Or if you look at any syllabi or any book, this is referred. Even I have seen in the GIAN book and other standard book, in Krajic's book, everywhere this reference is there, and it is included, and it is taught. But look at how he got the idea that iterate of a map is contraction. Map may not be contraction. Still you can have the fixed point, and still you can have the unique fixed point. And this very result you can use in many ways. I have sometimes used it also. Just look at, yesterday we were talking about the Dirichlet function. Professor Khamsi was talking about the Dirichlet function, and we all know, as far as my experience is concerned, only Khamsi can define Dirichlet function. Everybody can, only Dirichlet can define Dirichlet function. I am trying to say that only Dirichlet can define the Dirichlet function. Just look at this magic. As you have seen, the wonderful thing what I come across during the teaching, the excitement, that Dirichlet function is a everywhere discontinuous function. Have you given thought to it? Some of you can help me to prove this very fact, that Dirichlet function is everywhere discontinuous. Idea, underlying idea. But here is a function which is not continuous at single point, everywhere discontinuous. And the idea of the proof is very simple. Some of you remember? What is the idea? Sequential. Definitely, you will require some way. As he said, is what the simple fact was, what if we can find a sequence of rational converging to every rational and vice versa. We can find a sequence of rational converging to irrational, also rational. That is the case. You know that, as you said, the theorem, very theorem you use is what xn converges to x implies txn converges to tx. What is here, which you can make this very point, that this very function, Dirichlet function, is not a contraction, and you can very easily realize this. Are you agreeing with me that Dirichlet function is not a continuous function? Is not a contraction. Contraction, as you see, contraction, you all I think are familiar the definition. Here dx txy there are two facts here. Look at this very ratio, this you give everything, and then this really ratio. So always having the meaningful things. And look at this ratio. This ratio may be more than 1, less than 1. X is not equal to y, sorry. X is not equal to y. So this very ratio you consider, and this gives everything. Like if it lies between 0 and 1 strict, then it is a contraction. And if it is strictly decreasing, you have the idea of the contractive map, as was discussed yesterday. This is a larger class. Okay. And then if you take k greater than 0, this is we call greater than 1, this we call as expansion. There also exists a literature on this also, that d of Tx Ty this you call as contract. What the point I am trying to make is what, that simple idea, this very fact is simple. I advise you, if you are having sincerity, then as a teacher you can even do such kinds of things. You can come across such kinds of things, they are of vital importance. This very fact, which was proved in 1968, very simple result, very simple proof. Because if T is a contraction, then T to the power n is a contraction, and T to the power n, if T to the power converse is otherwise. This very theorem takes care of the converse. T to the power k is a contraction, then still T has a unique fixed point, where on a complete metric space. So otherwise the idea is different. Like this very theorem, what I said, Dirichlet function cannot be covered by Banach contraction principle, but Dirichlet function can be covered by this very simple result. This result has come in American Mathematical Monthly, 1968. That if T to the power n is a contraction, here I have taken T square, but T to the power n is a contraction, then still T has a unique fixed point on a complete metric space. And this idea I have used in many ways. Or you can also use this idea, like if you take T square, this you can replace by T1, T2, and you still have two classes, and then you have class of functions. So this very idea you can use here, like T square, now you can replace this T1, T2, and then of course still you have two classes like T to the power T to the power Q, and you can work with this class of mappings. And you still having the commutative definition, you can always find the fixed point. And the root of this function lies, those who are familiar with the literature, this goes back, trace back to Junk's fixed point theorem. From there you take a pair of map. This result has come in 1976, that Banach theorem or Banach contraction principle, this can be extended to a pair of mappings. So you look at how trivially this goes on. This is not very difficult. How we are writing our theses these days for our doctoral award, very simple. You class this, generalize, and you can go on doing this thing. And look at here, if you look at classically, sometimes you realize that this is not that significant. Thereafter, when people used to pursue it, it looks more significant, as if it is very, very novel. So his theorem is what, just look at the matter of the fact is what here, commutative is a condition, but this is not that business. But this very result, what I have said here, if T to the power n is a contraction, this is used in our MSc classes also. Then on the complete metric space, this contraction, this very idea is used in our MSc class also, like our Picard's theorem, that is also extended to this class, and that you can see for this even your Krajic's books. So this very theorem, like Picard's theorem, you all teach, I think so. So Picard theorem, you teach differential equations for this existence of uniqueness solution, existence and uniqueness of the fixed point of the solution. But if you look at the strongest point of the Banach contraction principle is what? That you can take a point x, you can create a iterate, its limit is fixed point. So there can be no simpler than this. If contractivity and completeness are there, you take any point x naught, create a iterate, find the limit, you will get the fixed point. That is the most simple. So this is why this theorem was proved. This theorem was so significant, and it can be used anywhere. Like I have said in the differential equations, Picard's theorem of the differential equation, you have a suitable condition. This very theorem enables you to what? Now you can take this for the power, any power of the map, and any power of the map, this class definitely covers a larger class. So the point I am trying to make here is that even simpler results sometimes, which you think they are not that significant, they go a long way. And they have the citations of the order of any order, like you look at this one here. One thing is related to my research life. When I was working here with Professor M.S. Khan, there I got a paper from Salvatore Sessa. He was very weak in English. He has sent me a paper where he has considered a very simple condition at that very juncture. I never realized it was that significant. The definition was, he was trying to enlarge the class of a commutative class, because it is there in Junk's theorem. And he has considered a very simple contractivity condition. He just used contractivity condition. And what he did is, look at the class. Suppose I take pair of map T S x, and this is obviously could be what here the possible gradient is what T x, T y, and so on and so forth. Initially, what he considered this. So, this could be equal to or greater than 0, because this is a often non-negative real number. This is also a non-negative real number. You have the comparison. What are the possibility? Salvatore is this class. Sorry, this is equal to this very class. No, sorry, still I am not correct. This is d of s x t y. Yes, s y, yes. S x t y t x s y. Look at this, could be greater than 0. This should be equal also, because two non-negative real numbers are comparable. And he sent me this paper to Professor Saeed M.S. Khan, with whom I was working. He gave me as a research scholar that you go through these books. I have read this paper and I have said this is a very good idea. He says, as I can say here, I can recall, तुम तो हर बात को अच्छा कहते रहते हो, ये कह के उन्होंने टाल दिया. What I did is, this was Italians are often not having good English. So, I have written with pencil this paper and corrected it in English. Its title was a junk type theorem, and I replaced it, the original title what is there, a weak commutativity condition in fixed point concentration. This is right I suggested, and I write everything, and the pencil line send it back, because that time you do not have the mail by post. So, I posted this very mail to him, and he published this paper in publication American Math Institute, Publication Institute, Belgrade. And I don't know, you can just verify, it has more than 1000 citations. Can you realize that very juncture, way back in this, I am talking 1982, maybe it has published in 1982. So, what I wish to say by this very instance, that you people may not feel that you cannot do good, still you can do good, and very simple, and often very simple and natural things are good, and they are later taken by, like you write a paper, or many of us are used to write a paper, some might be a paper you do not expect that this will be that good, and later it turns out to be very good. Why? Because it is pursued by many, because it attracts the considerable, and after this there is a history, I do not want to go into that, because that is very technical. That any common fixed point theorem is bound to have, common fixed point theorem means two maps involved, and there exists a point x such that there is a 2 points remain fixed under S and T. So, that is the case you have, but that is not very significant. Obviously, the original theorems are what just involving one map, but that is true is a way of literature. What I am saying, that never feel discouraged, never feel in disgust, always carry on the journey, and of course, with composed and considerate and focused manner. What is very important is focused. In mathematics, you are always required to be focused, and try to teach another thing which I wish to say, try to teach as many courses as you can. This is one thing I would like to say, because this is not very often taken by the candidates, by the youngsters. What you see, that if you teach many courses, you have the idea from the other, your vision is broad, Like if you are on the first floor, you see some part of your locality. If you are the fourth floor, you look at better about your locality, and when you go higher, you have more wide open vision. So as long as you read many courses, they give you the idea for the other course, and you get stronger, because as you know that many coaches in the games, I have read many where they adopt that means. I have read about a volleyball team, what they did while they were practicing, they were added with some weight. So, they have some weight while practicing. When there is a match, those loads were removed, and they are feeling lighter and doing better. So, if you apply yourself through this process, as I have said, what I am able to say this, because I have taught many courses. Like measure theory, I have taught measure theory. Measure theory is very difficult to teach, because it involves many things. It is not so simple, because but idea is very simple. Can you, some of you can share what is the idea of a measure? कुछ भी जो भी है, whatever you feel. Length means what? Length, no. Length is generalization of a length is your metric. That is metric, how metric you define. No, it is the idea is what, that if you have an interval, you have a length. Look at, if you go through this, better motivation you have in the Rana's book, because generally the standard books, they never care about this. If you go through this, you find the most easily read book is by S.K. Barbarian. That is very simple to read. We can go straight away and read S.K. Barbarian, because you do not need too much, but it has other ideas. As I have said in the beginning, that you cannot frequently change the book. You book from one book to another, it is not so simple to pass through. Like Halmos book and Barbarian book is somewhat compatible, because they use the same idea, like sigma ring and ring, or sometimes semi algebra. But look at the Reurings book, it used to always use sigma ring and sigma algebra. So their facts are, their class of subsets are definitely different, and they cannot pass from one book to the other. As I have said, that most readable book is S.K. Barbarian, and the best book you have is still, I feel, is the Reurings book. But the idea is what, just you have the length of an interval, as you have in the case. What about the other sets in the real line first, and later what was the idea of the measure is what, can we associate a length to every set and to a general set, because you go thereafter to a general set. And salient properties are what door on the real line or the real interval, because you look at, he has considered the intervals, Rana's book, before starting anything, he has collected the intervals and look at these properties like pairwise disjoint, and how about the commutativity property and other things. So, what is the thing over there, what background do you require? And I have read somewhere that Henry Lebesgue is considered as one of the most solid mathematicians. Some people used to keep him in the class of Newton, Einstein. Why? Because you cannot have another example of a generalization which is so significant. Look at the Riemann integration, the generalization of the Riemann integration to the extent of Henry Lebesgue. Just look at here, and so significant that is a part of our syllabi. What Henry Lebesgue did actually, that he extended that, look at, we are talking about the Dirichlet function. He was able to integrate a Dirichlet function. Like Dirichlet function is measurable. Look at such a typical function is still measurable. And what is there? The commitment, devotion, and the way we used to have our training. Like these days, our individuals, our youngsters having relatively poor background, they are not able to have education properly. But actually, they have the motivation. Like Henry Lebesgue was also coming from a very poor family, and he was taught by his fellow men, by his neighbors, by his town people. He was not having enough support. This I have read somewhere. He was educated with the help of his town fellow, or his inhabitants of that very town, who helped the education of Henry Lebesgue. But look at the impact he has made. or if you look at the Lebesgue integration or its overall impact on the mathematics. If you go beyond sophisticated mathematics, now there are participants. Dhage Saab, where is Professor Dhage? No, he used to write sometime even papers on differential equations involving Lebesgue integration. Like most of the time of the differential equation we are using, they involve what? They involve Riemann integration, but there exists a literature, there is a subject which uses Lebesgue integration as far as the differential equation is concerned. So also research in those directions also used to function, used to progress, and measure theory itself is the research domain. You can just look at, and all the basic things you just look at, and if you go beyond to everything, one cannot avoid as a teacher real analysis. Can you avoid real analysis? Obviously no, because real analysis can be a background to all mathematics, even calculus, the very first course. If you are not confident, if you are not well versed with real analysis, you cannot teach even calculus confidently or honestly. So overall, the point I was making is what you all, most of are young, you don't avoid to teach the course. As soon as you find a chance, you grab it. Maybe you are having time, hard time, but still you will be a different person, you will be an improved person. That is what the point I wish to make by dint of my experience, not anything else, that if I have something this, because I have taught many courses, almost algebra, I was very fond of algebra, I used to teach algebra also. With the linear algebra, I cannot say what I have not taught, I have taught most of the courses, and this helps me because I can appreciate anything you are talking, I can appreciate, maybe successfully or unsuccessfully, but I can appreciate. So क्या मुझे बैठना था, तो मैं एक शेर पढ़ देता हूँ, बहुत आसान है. मिटा दो अपनी हस्ती को, मिटा दो अपनी हस्ती को, अगर कुछ मर्तबा चाहो, ये दाना खाक में मिलकर गुले गुलजार होता है. मतलब समझ गया? Okay. The translation is very simple. When we used to crop our crops in the field, always see what will happen to the seeds. This is the idea. Seed का क्या होता है? Seed तो उसकी तो हैसियत ख़त्म हो जाती है ना. जो बीज होता है वो तो बेचारा ख़त्म हो जाता है, मगर उसके बाद सब्ज़ा उगता है, उसके बाद फसल लहलहाती है, तो बीज का वजूद ख़त्म हो जाता है और उसके बाद फसल उगती है. तो ऐसे ही कोई काम इतनी आसानी से नहीं होता है. जैसे मैंने कल शेर पढ़ा था आपको उसके लिए कि मेहनत करनी पड़ेगी, कुछ भी करेंगे तो आपकी फसल ज़रूर लहलाएगी. और मैं तो ऐसा मानता हूं कि अगर एक बहुत मेहनती आदमी है तो वो अच्छा खासा टैलेंटेड आदमी को भी सरपास कर सकता है. और मैं कमज़ोर होने के नाते हमेशा जो हार्ड वर्किंग लोग थे उनको पसंद करता था. वे जो बहुत ज़हीन है, छोड़िए उनकी बात, वो क्या करेंगे. जैसे आप देखिए तो मुझे एग्जाम्पल याद आ रही है श्रीनिवासा रामानुजन की. हार्डी ने लिखा था, GH हार्डी की बात कर रहा हूँ, GH हार्डी ने लिखा था कि अगर मुझे रैंकिंग करनी हो तो आई विल रैंक रामानुजन or I will award him 90, more than 90 marks. I will award myself, GH Hardy was awarding himself to 40 marks, and even to great Littlewood 60 marks, and our Ramanujan, great Ramanujan, 90 marks, any marks between 90 and 100. Not because of he was very good mathematician, but he was so brilliant. So it's just because mental power. So whatever is given from the destiny, we cannot change this. Maybe we are in the class of Hardy or even below, but still we can try and do some good mathematics. And at least not, because I remember my teachers here, most of them, my favorite teachers, they were not brilliant. I cannot cut them. Here my colleagues, Dr. Javid, Dr. Asif, Dr. Izhar, they all know, they were also their teachers. They are not very brilliant, but they are wonderful teachers and so sincere teachers. So only what we can do, we can do our job sincerely. It is not in our control that we can say that I am doing wonderfully certain things, I am great, or so many things. You cannot do that. You can just go and work sincerely. This is what is the. And one English mathematician told me that you Indians know how to spoil the talent. He framed this very charge, And he said in this connection that the world will not be knowing Ramanujan today if we have not made this possible. So Ramanujan is known because of Hardy and because of we people, not because of you Indians, because you know how to destroy talent. So this is all is there. But what is here, we are working for a common job, and जैसा मैंने वो कहा था कि भाई कभी कभी कोई बड़ा पैदा होता है, मगर हम मिल के सब कुछ ना कुछ कर सकते हैं. तो हमें कुछ ना कुछ करने की कोशिश करना चाहिए. बकिया चीज़ें हमारे हाथ में नहीं हैं. हम अपनी क्लास में तैयारी हुई, हमने जावेद से कहा कि भाई ऐसे बोल रहे हो, वैसे हम कैसे बोल सकते हैं. सुबह उन्होंने कहा भाई आपको इंगेज करना कोई टेक्निकल बात में तो और मुश्किल है. जो टेक्निकल बात जो मैथमेटिक्स करता है वो टेक्निकल बात कैसे नहीं कर सकता, उसको करना ही पड़ेगा. तो आप देखेंगे जैसे रिसर्च भी है, यहाँ भी कई चीज़ें ऐसी हैं जो होती हैं, और जब शुरू में दिखता है, जैसे कल आपने बहुत सारे आइडियाज़ देखे हैं जो बना कंस्ट्रक्शन को प्रूव करते हैं, उसके प्रूफ को छोड़िए, जो उन लोगों ने किया है वो देखिए, तो आइडियाज़ उतने मुश्किल नहीं हैं. एक्सेप्ट कि जो ट्रेजडी वो कल वो बयान कर रहे थे खमसी साहब, किसके लिए, फॉर कैरेस्टी. So sometimes such tragedy happens, but obviously this is not often the case. So our job is to work sincerely to our respective goal, and we all are one in every sense, you know, because we all work for a common cause. Similarly, teaching is also a common cause. We used to train our youngsters, and it is their duty to take care of what is over here. Because if you come from why I am referring all the time from a background, because your need also compel you to work hard. If you don't have that kind of need, like if you are very prosperous, maybe this very salary is very wretched, you don't want to work hard. What to do? I don't want this of money. This is happening. As sometimes you see many students in a private university, they are not that devoted and involved. So devotion is the main thing. So we should have our devotion. With these words, I thank you for tolerating so many minutes. Thank you. अगर आप में से कोई कुछ कहना चाहे तो मैं सुनना पसंद करूंगा.
सर कुछ मैथमेटिकल फिजिक्स के बारे में बोले.
देखिए मैथमेटिकल फिजिक्स में मुझे बहुत तजर्बा नहीं, मगर मैं बोल देता हूँ एक लफ्ज़. हाँ चलिए, हाँ ठीक है, मैं बोल देता हूँ. देखिए ऐसा है कि आपने देखा है बगैर मैथमेटिक्स के फिजिक्स पॉसिबल नहीं है. अब मैं अपने पुराने टीचर को याद करता हूँ फिर. This very room has the lectures on axiom of quantum mechanics. I have heard in this very room the axiom of quantum mechanics, and axiom of quantum mechanics cannot be understood, cannot be appreciated without the theory of operators. Those all theory of operators. Like what is operator? And physics people, they were explaining, and we were appreciating it better. So this all internal quantum mechanics, they are using better mathematics than what we know today. Even many theorems, like in economics, I used to say, there are the mathematics which are used in economics. Even we are not going to teach it in our MSc classes today. So that kind of mathematics is used. So physics and mathematics, physics is not possible without mathematics, and they know better mathematics than us, as far as that very thing which they use. So that is the language. As you see, our teacher used to say, mathematics is the language of all sciences, but to my mind, mathematics is not possible without physics. Physics is not possible without mathematics. Yes.
I have two questions.
Yes.
One is that you said almost every paper I have taught of the departments. Have you ever tried, or have you get the chance to teach the differential geometry or differential?
Yes, very true. It's a good question. I have taught this very thing, and the story is very interesting. I was teaching as a young student BSc final. I asked to teach the half part of this, that is advanced calculus of several variables. 1 or 2 years I have taught. Professor Mohsin came along and pushed me to differential geometry DG. So yes, I have taught DG using David Witter. Yes, using David Witter.
You said work hard. Actually, our obviously we all are going to be the teacher. They all are going to be teacher. So what do you think for a teacher, or for as a duty of the teacher is doing hard work, very hard work is more important, or to execute is more important? I mean, how much we are producing to the students, that is important, or you think we are inherent qualities, we are working very hard, we have our own knowledge, but as compared to others, we are lesser expressive.
I got your point. Because when you start reading, teaching mathematics, every day you have some problem. Suppose I am trying to prepare 5 lecture for tomorrow, and that is a new subject. I may have 1 or 2, 3 questions. And it is said that if you are a mathematician, you must go to the bed with a problem. Maybe you get up also with that problem. So you must always have in your mind a problem. And whenever you teach new things, you will always have a problem. My friendship with Mohamed is what? This is the only thing I can share with him anything. And why I like? Because if he will reply, he will give something positive, otherwise he will keep mum. He will never say anything irrelevant. His quality is not that he will give you it. His quality is he will never speak irrelevant in mathematics. So first thing is what? Always any mathematical reading, that must be accompanied by a good discussion. Like Dr. Asif is here, Dr. Javid is here, whoever is your company. First you discuss in your company, then go to the next level. Your senior teachers from whom you expect you can get an answer. So your talent alone you will not get the success, as I mentioned yesterday. You are very talented, but you are not doing that well. Our teacher, Professor Izhar Hussain, was a very, very, very intelligent person. After this, I don't want to say he was very sharp. He was sharper than anybody else in the department. So alone your mental strength, mental power will not ensure you success. And if this is the case, how Einstein was so successful? A person who forgets his home, who forgets where he is visiting, where he is going, how he can be so wonderful? Look at his achievements are before us. So involvement. So our involvement should be of that very kind. Maybe we are not, but our involvement should be of the order that we discuss whatever is required in our lecture. Tomorrow I am going to teach something. Like once I was talking to Professor Nur Muhammad, how will you have 2 then sets? He immediately said, dxy equal to or less than epsilon. If you can find for any 2 points, a point x, another point y, said that norm of x minus y is less than epsilon. This is denseness. मतलब आप किसी भी पॉइंट के जितने करीब चाहें दूसरा पॉइंट मिल जाए, दिस इज डेंसनेस. As you see, rational numbers are dense in real line. Have you given thought to this? Dense, why it is dense? It may be another big set which is not dense. So idea. So what is there, Dr. Musawwir, you have this idea, you will appreciate what I am saying. The virtues cannot be learned. The virtues cannot be taught, they can be learned only. There are many things in mathematics जो पढ़ाई नहीं जा सकती है, वो आपको खुद से सीखना है. So everything cannot be communicated. Like if you take the example of the limit, and at our level, in our scenario, limit, the notion of the limit is a virtue. It cannot be communicated. किसी दिन आप खुद ही समझ जाएंगे क्या होता है. आप बच्चों को बताएंगे वो कैसे समझता है. So there are certain notions in every subject which cannot be communicated, which can be learned only. So that you try to do. What is there?
Actually, I asked the question due to my greediness, I should say. I could not attend your lecture yesterday.
I am not giving any lecture. I have just shared my experience.
Your lecture, your speech actually. I was on the stage, so my mind was.
Like what?
Today also I was.
You can verify from.
Listen more to you.
What you can verify. I initially don't want to give this very meeting, this format, because I am not prepared. I have to have the preparation before I come to the audience. And this has been taught by our teachers, Professor Mohsin, Professor Hussain. Don't go without preparation in the classroom. Always have the preparation, and then go to the classroom. And you always anticipate what are the possible questions on this very topic, or what the questions boys can ask. Maybe still you can have the boys. One day I was teaching +2, as you know, here we teach +2. A student stood up and asked, why these trigonometric ratios are 6 only? एक लड़के ने पूछा, बहुत ट्रिवियल सवाल है, अगर हम बता दें, मगर मुझे 1 मिनट लगा उसको सोचने में कि ये 6 ही क्यों है ट्रिग्नोमेट्रिक रेशियोज. कुछ दिया उसने, अब ये तो एक्सपेक्ट नहीं करते आप, उसने कह दिया. हो सकता है आप जवाब दे पाए ना दे पाए. तो लड़के भी कम ज़हीन नहीं होते हैं, बात बहुत ज़हीन होते हैं. ये मत समझिए आपके लड़के कोई इसमें हो सकता है कोई आपसे बहुत ज़्यादा ज़हीन हो. तो ज़हानत तो ऊपर वाले की दी हुई चीज़ है, हम तो अपनी बात करते हैं, अपनी बात करिए। और आप लोग सभी लोग अच्छा कर रहे हैं कि मैथमेटिक्स में जो लोग आते हैं वो अक्सर मेहनती होते हैं। मैथमेटिक्स में वो आदमी जो मेहनती ना हो कम ही आता है। लेकिन दो चीज़ें जो हमारे टीचर ने कहती वही कहूँगा मैं, ऑलवेज डिस्कस मैथमेटिक्स, नॉट एलोन अपने तक मत रखिए, उसको फैलाइए। तो वो उसका यह है कि दूसरे लोग सवाल पूछें। जैसे हमने आपसे कोई सवाल पूछा तो हमें लगा कि हमें तो मालूम नहीं है, फलां को पता चल जाएगा कि इमदाद खां को मालूम नहीं है तो ये छोड़ दीजिए, नहीं मालूम है तो ठीक है, पता चल जाएगा। ओके, स्टिल समथिंग यू somebody wish to say? I would like to hear. चलो ठीक है। Thank you very much for giving this very opportunity. अरे एक प्रॉब्लम और हो रही है कि हम लोग जो है इसके लिए आउटडेटेड है।
तो भैया ए जुनैद,
ये आपका
रिकॉर्डिंग के लिए
हेलो नॉर्मल की हेलो हेलो मैं हूँ फराज और आप देख रहे हैं हमारे साथ ज्ञान को
Am I audible? Okay. So this is a tutorial session, and I will just recall or basically some results, well-known results from the fixed point theory, or you can say not so many, a few classical results. Some of them already discussed, but I want to give a basically broad spectrum of the fixed point theory, means what are the other directions or like that. So of course majority of these stand basically from the fixed point theory background. So there is no need to just give the basically formal definition and other things example. But of course as you know that what the mean by fixed point theorem. Fixed point theorem means that you can say it's a basically mathematical statement under which we have the guarantee of existence of a fixed point of a given map defined on a non-empty set. Because we know that several examples from the literature, and of course there are so many examples still in the literature, they don't have a basically fixed point. For example, if I consider a just translation map, so of course this does not have a basically fixed point. So it means that so that's why we need some concrete statement, a mathematical concrete statement, so we can say the guarantee of existence of a fixed point. And of course other time this uniqueness is also important, is basically due to application, because in some application we need the uniqueness of a solution. Of course in some problem there is no need of the uniqueness. For example, in the optimization problems there is no need of the uniqueness, but of course in the system of linear equation and some other differential equation, of course the solution is unique, so that's why we need the basically uniqueness of the solution as well. So two important issue, one is the existence. So we have, for that we have a basically translation map. So because this does not have a fixed point, so that's why we need a concrete statement. If we have a fixed point, whether this fixed point is unique or not, then again we have a basically another counter example, that is identity operator or identity map. Every point of this map is a basically fixed point. So these are the issues. So just as of course Professor Khamsi already told us, basically a lot of hidden secret, or you can say discussion from the literature, but of course this idea of the fixed point is basically a very old one, because as he pointed out that initially it was not basically in the form of a fixed point theorem, or you can say result, or even definition of a metric space. Of course Frese introduced this concept, but systematic definition given by Hausdorff later on, maybe after maybe something 9 years or 10 years, 8 or 9 years. Same, initially basically Banach proved this theorem on a continuous function space, because he was not a mathematician, he was a basically computer engineer. Banach was not a mathematician initially, he was a computer scientist. So but later on Banach give that of course means once we have the notion of metric space, then we have this theorem in the particular, or you can say specific statement, every contraction on a complete metric space has a unique fixed point. So my point was here, this theory is basically very old, and we can see its basically presence in the work of French mathematician Henri Poincare. And of course again he was not a basically a fixed point theorist or like that one, because his research area was something mechanics and mathematical analysis. So basically he used or utilized this approach to study this kind of the problem. Okay, and as we know that this is one of the important branch in mathematics, modern mathematics we can say. Reason is that due to the application, of course mathematical part is very important, and we can say this is basically bridge between the pure and applied mathematics, because on the one side we have a very nice and very important and very deep result in mathematics. On the other side we have a very important application in the diverse field of mathematics, even outside the mathematics, especially in the computer science, in the economics, and in other areas, even in chemistry as well nowadays. So that's why generally people now considering this subject as a bridge between the pure and applied mathematics. Okay. Now this basically just I want to recall a property that is topological property, means which is invariant under the homeomorphism. Okay, so such property is called the basically topological property. So fortunately, this property, fixed point property. So what do I mean by fixed point property? Of course, in general, we can say if every continuous map defined on a topological space has at least one fixed point or not. But in particular, we just state this property for non-expansive map, because every non-expansive map is also continuous map. So this is called, so a topological space is set to fixed point property if every non-expansive map has at least one fixed point. So whether this is a basically topological property or not. So answer is yes, fortunate. So so this is a basically just simple observation. This is a basically topological property. So suppose T is a basically my homomorphism from X to Y, and S is where any continuous map from Y to Y. And now consider the basically composite map here. So of course this capital F is basically T inverse ST is again a basically continuous map, because composition of a continuous map is continuous map from X to X itself, now self map. So so if X naught remains the basically fixed point of F, and if suppose X naught is the basically fixed point of F, Y denotes image of the X naught under T, then F of X naught just operate at X naught both sides. So T inverse of ST of this. So T this T X naught is basically just we, but of course this is a fixed point, and now we operate the T both sides. So when once we operate the T both sides, so T inverse ST of this one is basically just T X naught, but this is identity, and now this is basically just my, I can say this is a Y naught, because Y naught is the image of X naught under T. So this becomes finally S of Y naught equals to just Y naught. And what was the this is, it was a basically continuous map. So it means that this ST of Y naught, or means you can say S of Y naught equals to Y naught. So which shows that this Y naught is the basically fixed point of continuous map S again. So once this continuous map F has a fixed point, then of course it is invariant under the basically another continuous. So that's why this is a basically topological property. Broadly, fixed point theory divided into these three major categories. Of course, one is the topological fixed point theorem, and second is the metric fixed point theorem. So basically, theme of this GIAN program is on this category, metric fixed point theory, because we are dealing the results in the either in Banach space and metric spaces, not in the basically just topological or algebraic topology and topological space. Another one is the discrete fixed point theory. So these are the basically three major category of fixed point. So just I want to just state basically some very famous and fundamental fixed point theorem from these categories from the literature. So already, of course, Professor Khamsi already delivered the, of course, 3 talks in this direction on Banach fixed point theorem, then its extension like Krusty fixed point theorem, then later on, of course, now he will start the basically fixed point theorem for the non-expansive map. So this is a you can say very important for this GIAN program and main theme of the GIAN program. But here I want to recall basically some important fixed point theorem from the other categories, which is from topological fixed point theory and discrete. So these first 3 theorems basically belong to this first category, topological fixed point theorem. And of course, this is the first fundamental and first fixed point theorem in this direction, and later on these are the basically extension of the Browder fixed point theorem. So what is the basically Browder fixed point theorem? Browder fixed point theorem says that if we have a continuous map which is defined on a closed unit wall in a Euclidean space, or you can say finite dimensional Banach space, then it has at least one fixed point. This is very of course, this is very natural result, and of course here you see this basically result basically for the continuous map, because in the case of metric fixed point theory we have a condition for contraction, contractive, non-expansive. So here class of the map is basically in general very large, that is continuous operator. But of course for that we need basically some extra conditions. Of course, Banach space is here, finite dimension, and we define basically this operator on a closed unit ball. But there are some other statement of this theorem. Generally, people also sometimes consider closed bounded convex subset of Rn. But here basically I just consider this operator on unit ball, closed unit ball. So of course that is bounded by default and it is basically convex. So so closed is already there. So boundedness and convexity is just by due to the definition of the ball. So that's why it is the same statement. Or sometimes some people say compact convex set of Rn. So compact convex again is the same thing, because in finite dimensional compact closeness and boundedness is the same thing. So anyway, so this is a very fundamental result which was proved by the Browder in 1912, and of course this theorem is very important in mathematics, but it has very nice application in the other branches. Especially if I recall the one famous application from the economics, because later on Professor John Nash basically utilized this theorem to prove the basically existence of the Nash equilibrium in the game theory and economic problem. And of course, you remember, so this is a Professor Browder and Professor John Nash. I think he died in 2015 something in New York, something, yes, 10 years, yes, 2015. And so just basically he basically gave the existence of the Nash equilibrium in the game theory and economics problem. As yesterday Professor Imdad say what the equilibrium problem, it's a basically intersection of the demand function and supply function. So always we have some saturation, and that point is a basically equilibrium point. So this theorem was useful, and of course for this study he got the basically Nobel Prize, of course, in the economics. And then again, as yesterday in the opening ceremony I also pointed out, still this theorem is very important. People basically prove its most complex and generalized form, and to study the basically again generalized equilibrium or Nash equilibrium for the complex games and problems. So in 2018 ICM, which was held in the Rio de Janeiro in Brazil. So this professor from MIT, Constantinos, got the basically this Rolf Nebula Prize, and of course this is the second highest prize after the Field Medal. So still people are basically working on this theorem, and even that time I met Professor Michael Atiyah, because of course he is also basically one of the field medalists, and later on he also awarded the Abel Prize as well. And just before his death, he also claimed that he proved the basically Riemann hypothesis. But of course, later on it was a false. So he again, when I met, and then I say, okay, I work in fixed point theory. Then he started with the fixed point theory in the topological groupoid, not in the Banach space or like, because his theorem is very famous for computation point of view. So and so this is a basically Browder fixed point theorem. And as Professor Imdad said, if we consider n equals to 1, so this is a very fundamental or basic result from in the real analysis at UZ level. Means if I consider C, means in place of Rn, n equals to 1 R, and if we consider any closed interval on R, then of course every continuous map has at least one fixed point. So this is basically my R, and of course if I consider C equals to some maybe 0 to 1 or A to B, doesn't matter, and if I have a map from C to C, of course this is subset of R, and of course closed, bounded, convex, no problem here, and this is a continuous map, then it says that T has at least one fixed point. So there are two proof of this one. One is a geometric approach, that is very obvious, and another is simply you can do the simple analysis. So in geometric, what we can do, just of course this is I think is the logo of our GIAN program. So proof is already here. We can see this is basically my identity function, and this is some continuous function. So if we have a basically identity map, and we have a continuous function from the same domain, then of course it will intersect the identity function at least one, and that intersection point is a basically fixed point of this. So this is very, of course, this is a basically picture from the very famous book, Fixed Point Theorem by D.R. Smart from Cambridge University, something long back, 1968, like that. So okay, on the funny side, I put this picture, but this is a very famous picture in the fixed point theory people generally use. Okay, so proof is already here. Whenever you have a continuous map, then that continuous map always, of course, on the same domain. Then at least it intersect this identity function at least one. So that's why it has a basically fixed point. Otherwise, analysis just we can do simple analysis. What we can define? We can define a some map from C to C again, and this is from again geometry. What we can do? So phi of x equals to just difference of this map Ix and minus identity operator. Just difference, or maybe I can say simply Tx minus x. No problem. So this is basically difference of the two continuous operator. So T is a continuous already, identity is a continuous operator, so that's why difference is again a continuous operator. So this is a continuous map from C to C, and if we see what is the basically just phi of A and phi of B. So this is T of A minus A, and this is T of B minus B, and map is basically my from A to B, closed interval A comma B to A comma B. So of course this greater than equals to, because image will be either minimum A or maybe more than A. So that's why this difference is always non-negative. And of course image may be maximum B or less than B. So that's why we have these two signs. Okay. So if I consider the basically equality sign here, suppose this is a equality sign. It means that or you can say phi of A equals to 0. It means that T of A equals to A, means this initial point is the fixed point. And suppose, so proof is over. And suppose again we have the equality here. So again basically T of B equals to B. So there is a fixed point of T. But on the other hand, if this is a basically strict sign, it may be like that. It means that we have a continuous map. On this initial point A, it is basically value is positive. On this point B, it has a basically negative sign. So we know that basically a very important theorem from analysis. I think so, intermediate value theorem. So if we have a continuous function, we change the sign between the 2 points, then it has at least one root. So it means that by the intermediate value theorem, there exists a basically you can say C, or maybe you can say Z in capital C, but not capital C, in open interval A comma B, because otherwise if same, such that phi of Z equals to Z. But what is the phi of G? Oh sorry, it has a solution or root. But what is the basically phi of Z? T of Z minus Z equals to 0, so T of Z equals to for Z. So again it is basically solved. So either we have a equality side and still we have a fixed point, otherwise simple analysis. So proof basically idea again from the basically geometric interface. So this is very natural result. Okay, and it has a lot of application, but important thing is that whenever we give this any result in mathematics, we always try to extend the given result for the bigger domains or maybe more important spaces. Because my space is finite dimensional, so of course application of this result is limited. So question was whether we can extend this result for a infinite dimension or arbitrary Banach spaces or not. This was a question. So of course, and why these infinite dimensional Banach spaces are important? Because these space of the continuous function, sequence spaces, all are the infinite dimensional, and we can characterize lot of things using this one. For example, for the space of continuous function, we study the basically solution of integral equation and differential equation, and so many other things. For sequence spacing, we can characterize the so many compact operator and like these type of the things. So that's why these arbitrary Banach spaces are very important. So of course, answer of means in general, answer was no. So for that, I think Kakutani gave a basically one counter example in L2 spaces and you can say in the C0 spaces. So so this was a example sequence space, just x equals to C naught, space of the all null sequences with supremum metric or norm, and if consider a closed unit ball in C naught and define a operator from P to B, something like that, T of x equals to, so x is basically sequence, so this is something 1 minus mod of x1 comma then x1 x2 so. Okay. And then so this is a simple exercise because this is a tutorial session. So now we prove that norm of Tx minus Ty equals to norm of x minus y, where of course for all x and y in B. Say isometry. So can we do it? Yes, maybe quickly, 2 minutes. Okay, this we give the basically this is a continuous map. So because I want to check whether a continuous map on a arbitrary Banach space or infinite Banach space has a fixed point or not. So we already consider this is a basically closed unit ball and convex. Only just this is enough. Of course, there are several ways to check continuity. We can also go through the continuity from here, but from here it is very trivial because since this is isometry, automatically it is a continuous map. Similar example in the L2 spaces. Similar example in the L2 spaces also here. With respect to supremum norm is there on C naught because this is a Banach space with respect to supremum norm. Of course, this is exercise from the book of Khamsi. Again, an introduction to metric metric and fixed point theory. Introduction to metric space. This is a very important book. So if you want, then I have a copy of this one, so maybe I can give you. Otherwise, very expensive book. I think maybe something 12,000 or 11,000 like that. Is it okay? Okay. So because this is a non-expensive or isometry, we can say also. So this is a continuous map because every contraction I see, every isometry, every non-expensive, all are the continuous map. Okay, so this is a continuous map and which is defined on a closed and bound ball. Suppose if we assume that this has a basically a fixed point, means Tx equals to x, then we have a contradiction to this fact 1 minus mod of this one. So if we assume T has a fixed point, then we lead to this contradiction 1 minus mod of x1 equals to 0. Just because we compare the coordinate from both sides and we will get the basically this contradiction, this part. It means that of this and this is not on the. So anyway, a similar example on this one. So question is that how we can extend this result for arbitrary Banach spaces. So of course, yesterday as I pointed out that we want to extend the class of operator from contraction to contraction, but on the time we reduce the basically space from complete to compactness. So in Schauder in 1930. Basically, he just basically give the means extend this theorem. So basically, in place of the this closed and bounded ball, he considered the compact subset of a Banach space. Because in R, compact and closed and bounded is same thing. So that's why. So just if we put this compact, that's why basically here I just put the basically this word only closed and bounded. Otherwise, some author put the basically compact here. So if I put the compact here, then you say, sir, what is the difference here? You already take the compact here and in the same. So basically, this is basically closed and bound is better. So what we can do? So now this is basically compact, because generally in infinite dimensional Banach space, ball need not be basically compact, because it's of course always a closed and bounded and convex, but that is not basically compact. So that's why this is a basic. And this theorem has lot of important means application, especially in the differential equation side, to show that basically exists. And Professor Dhage is here. I think you also utilize this theorem several times in your basically existence results and like this. So this was a very important theorem. Okay. Professor Amine already discussed this part, so I am not going to this part. But and of course now tomorrow he will discuss these two theorems, because just today I think stopped here, maybe on the Gaude theorem, because I think till now he did not mention the basically Kerr theorem about the normal structure and reflexivity. So only just he stated non-expansive map, because class of the non-expansive map is bigger than contraction, as we know that, but there is no guarantee of the fixed point of a non-expansive map. For example, like translation map again. So that's why we need some concrete statement which gives the basically guarantee. So of course these theorem will be basically discussed in the coming days, in three coming days. So that's why I am not going to discuss these theorem. But I want to just basically so I just basically here point out the third category, that is the discrete metric fixed point theorem. So this is the man Tarski. Basically, he basically proved without any just metric and underlying topology. Just basically, this is a discrete version of the, or you can say discrete analog of fixed point results. So what basically he proved? Okay, he considered the basically complete lattice, and it's a basically F is a order preserving map. No continuity on this one, because we don't have any topology here. So just why this order preserving map means x is less than y, means whatever the order there, and then of course f of x, y length. Then set of fixed point is of f is basically non-empty, and even that is also a complete lattice. So this is very useful in the computer science and other area in the mathematics. As we say that of course we always interested in the you can say generalization extension. So on the other side, so these all theorems basically. And of course, after that, this order, after that, Tychonoff basically extend this theorem's order to the locally convex spaces, that is more general spaces. So this is basically another important generalization and very useful in the other areas. Okay. So as I said, we always looking basically just to study the theorems or problem in the more general setting for more general operator. So that's why fixed point theorem for the multi-valued map is also very important. So this is another research area. So this theorem, Banach fixed point theorem, is already extended for the multi-valued maps, because multi-valued maps describe the lot of problems from economics, from the game theory, from the computer science, from the fractal theory, and differential inclusions in the differential equation. By differential equation, but we have the containment that is called the basically differential inclusion problem. So that basically is studied by the basically multi-valued map. So for the multi-valued map, we have a of course total means complete side of the story. So, but what I want to say here, just this Banach fixed point theorem already extended to the multi-valued map by the Nadler in 1965. And one very important here, because Khamsi was saying 1965 revolution. So this was not the basically revolution only for the non-expansive map. Lot of important results appeared from 62 or 63 to 72, like Eldestine theorem, because from Banach theorem was proved in the 1922, and after 1922 Eldestine proved his result in almost 62 and 65, and then Kerr theorem, Gaude theorem, Browder theorem 65, and this Nadler theorem in 1969, 69, and then so these 10 years were very productive, or you can say. So that's why. So Banach theorem basically extended for the multi-valued maps by the Nadler, and of course later on in fractals, that theorem is very useful to generate the basically fractal. Collet theorem is there. So people from the computer science, so you can generate the attractors or you can say fractals using the Collag theorem. So that is total application of the Nadler fixed point theorem, multi-valued version of the Banach fixed point theorem. Okay, and so now if I come to the basically non-expensive part, so of course Browder theorem is also extended or proof for the multi-valued map. Lim is basically give the basically extension. And of course this theorem will be discussed in the coming days, but for the Kerr theorem this problem is still open problem for the multi-valued map. So this is very important problem still. Of course there are some partial answer in some particular specific setting given by the people from the University of Sevilla, Spain, or some Polish mathematician, but still this problem is open for the multi-valued map. So this is a very important problem. So what is this? This is the Kerr theorem. If we have a non-expansive map which is defined on a closed bounded convex subset of a reflexive Banach space with this geometric structure that is called a normal structure, it has a basically fixed point. So still this problem is open in this area. So this is another problem. So of course we have to think about this problem. Just if I can 3 o'clock. So, just I stop here. Another important thing, Professor Khamsi explained, or you can say talked about lot of things about the Kerr-Stee theorem. I think maybe 10 times in a day or maybe 15 times like that every time. And of course, I have one book. Depend be a you can think again same thing as Amine say that just I want or want a different proof of the Banach theorem. So let's open the door, and after that the story is there. So same thing that proof is also very natural by given by the Chirich. So I stop here because we have to go to university visit just for a few hours, maybe 2.5 3 hours. So now I stop here, and tomorrow we will continue.
Two quick question.
Yes.
Where we can found the proof of Browder fixed point theorem.
Which one? In general?
General. Yeah.
Yeah, in the one proof is for r equals to 2 is given in the basically DR Smart book also. Yes.
For general RM, for not restricted.
Of course, in his paper, but I cannot say in general.
So this is every time people usually say that Browder fixed point theorem is one of the first fixed point theorem, but I believe that almost everywhere nil. People don't know the proof for a general setting, so
General setting is very
we all should look at this. As the research is still on.
No, in TVS proof is given. In topological vector space setting is proof is available.
There is one very interesting remark by
सही पर
70 years of Browder fixed point theorem, and then 90 years of Browder fixed point theorem.
even I think 100 maybe.
And 2014, there is a one proof given by Professor Sompom Domponsa, a shorter proof of Browder fixed point theorem. Another proof given by Hisham bin Makhail, a shorter proof of Browder fixed point theorem. So it's so profound, even though I was discussing.
So that's why I say na, so,
even myself did not see the proof of Browder fixed point theorem.
original.
I was discussing with him. Did you see? So he was saying no. So at least because we are the fixed point theory people, we should see the proof. It is a different ball game. It is understandable to us or not, but at least we should see. Oh, this is the proof for general.
It is in finite dimensional spaces.
Yeah.
So it's not going to be useful. It's not going to be finite dimensional space.
No, that's a different video, but he is asking whether we have gone through the proof or not.
But
This was the simple question.
It is difficult for high dimension.
Yeah.
R1, R2 are okay.
Yes, R2 up to R2 using the simplex and this one
But
proof
for
are
high
available.
difficult.
For iron,
Algebraic topology and so on. So it requires.
when you see the proof, generic proof, you all should see at least one margin.
So this is a part of research. Okay, this is a one proof, may be difficult, but people came with a different idea, as he mentioned. Sahi Park and others, Hashem and Sompong, they came through the different. So for example, as I Chirik also proved obviously this Kresky theorem just using 100% analysis, no algebraic approach. So this is also part.
So there are any generalization of Schauder fixed point theorem to know complex space or a small class of complex space.
Yes, there is basically generalization that is known as the Darboux fixed point theorem. Yes, because where we relax obviously this compact, because of course compactness relation is very hard. So this is generalization, that theorem is known as the Darboux fixed point theorem, and that is very useful in the differential equation.
Please ask the question.
Using measure of non-compactness. Yes. They basically reduce the this compactness.
Narendra bhai, you should ask something.
Again, there is one
You
more
are senior, so we can ask.
But your question was not the question, it was the information.
But it's very exciting book. Only 2.5 page by Sompom Domponsa. And Hisham is more.
सर यहीं पे रखूँगा इसको क्या